Okay, so start. Okay, so last time basically what I wanted to show is that there is a vast number of phenomena where people are interested in statistics of energy levels, statistics of wave functions. Essentially, this is kind of phenomena where fluctuations are important, and one has to know what to expect of the system. For that, one should know the statistics. Then I showed that it is possible to measure both statistics of eigenvalues and statistics of eigenfunctions. And then I argued that there is really a large, a broad universality class where approximately rotation of the basis doesn't change statistics. And this is the realm of classical random matrix theory of Wigner and Dice. But today I want to go beyond and announce what, also without going much into details, which I will go later on, what is beyond of that, what is beyond of the realm of classical random matrix theory. And this is mostly the phenomenon which is known as Anderson localization, and it is known for 60 years, but still it is evolving from localization in three-dimensional system to localization in low-dimensional system to localization in the extremely high-dimensional system, which is the Hilbert space of interacting systems, and then eventually to model such high-dimensional space, it is now interesting what happens to localization on the graphs, like a Kelly tree, like so-called random regular graph. So this is what we'll follow later on. But now I'm just showing the simplest example where this localization was discovered and it started from. And this is the situation where there are some impurities in the condensed matter system, in the system of electrons which are weakly interacting. And then we know that if there's no impurities, there's a plane waves. And then if the boundary is complex, then there is a billiard. But if we put here some scatterers, then situation may change. And if the density of scatterers is strong enough and the amplitude of scattering is also strong enough, then Anderson had shown more than 60 years ago then that the wave function may become like this. So it has some available volume. In principle, it can be located anywhere, but in fact it chooses one particular place, center of localization, where this wave function is large, and everywhere beyond it is normally exponentially small. So I told you that one of the test experiments is the experiments on the microwave, and role of impurities are such bumps on this microwave resonator, and also one can probe this intensity of electromagnetic field and see the pictures similar to that. So this is the old picture of localization. For those who are not very familiar with that, I want to emphasize the difference between the let's say Fabry-Perot interferometer, where the waves there is two propagating waves in the opposite direction, they interfere, and as a result this this light is trapped between the two almost ideal mirrors. But then what is Anderson localization is not like this, because this for electrons it would be a trapping in, let's say, potential well. So it is also localization in the sense that the density of electrons is only located between the inside the well, but in fact Anderson localization is more reminiscent of the situation where there are not two strongly reflecting mirrors, but many weakly reflecting mirrors, semi-transparent. Then there is interference, of course, but interference at multiple scattering, not just two waves interfere, but interference is at the multiple scattering. And this is the situation which happens in one-dimensional system with Anderson localization. And what has been shown that if the system is one-dimensional, then even arbitrarily weak reflection in a long enough system leads to the concentration of intensity in some finite portion of the volume. So this is the difference between the trapping in a well and the Anderson localization, or if you wish, Fabry-Perot interferometer and such multiple scattering. So then I would like to say that there was kind of revival of Anderson localization, which was put forward in 1958, and it was some kind of revival recently related with two things. So one thing is experimental. This means until now, but mostly, let's say, 10 years from now, 15 years from now, there was a great breakthrough, experimental breakthrough, where people could be able to make a laser cooling of atoms, and then they could cool system of atoms to the temperatures as low as 10 to minus 9 Kelvin. And then such atoms, which are real atoms, heavy, like rubidium, they show the properties of the waves, like quantum mechanics suggests. And then it is possible to observe localization of so-called cold atoms. So what people do, people take this collection of the atoms, put them in a laser in the laser trap, so they can model lattices, they can model interaction between this. So it is a very clean system where there is no any environment, because it is everything in the vacuum. Then there is no phonons, and so there is a clean system of particles. And if you initially concentrate this particle by the strong trapping potential, laser potential, in one point, and then release this potential, then what happens is that in the geometry where particles cannot escape other than along a one-dimensional direction, then the particle do not escape, in fact, if disorder is strong enough, and are also concentrated in some point of this one-dimensional structure, and this is something that can be tuned, because the disorder potential is made by a very simple thing. So you have a laser beam, and then you have the glass with many scattering, what is in Russian called milky glass, and then the laser beam splits by many rays, and they produce some picture of the bright and dark spots, so-called speckles, and this is the disorder in this system, because the energy of a particle depends on the intensity of the applied laser field. So one can model not only crystal, but one model disorder in this crystal, one model interaction, and Anderson localization was observed in this situation, which somehow, conceptually it is clear, because we know that even a heavy particle display wave properties of the waves, but somehow for these people of atomic physics who actually developed this experimental technique, so for them it was just, they read these papers about Anderson localization, and somehow they say, well, okay, for electrons it is probably okay, it is with light and so on, but for atoms, how atom can be trapped by weak disorder. But then they did this experiment and convinced themselves that this is indeed the case. I know that from first hand, because Alain Aspect, who is actually Nobel Prize winner, not for this, but for other achievements, he made the most spectacular experiments in Orsay, and he told me how was he as an experimentalist, how was he surprised and happy when he saw things like that. Okay, so this is now a bit more some comment. The comment is the following. So when wave functions are localized, then we can imagine a picture like this, that one wave function is localized here, the other is localized there, the third is localized somewhere else. So these are all different wave functions. But if I take the linear combination of such wave functions, and we know that let's say if the Hamiltonian is random matrix and there is n by n matrix, then there are exactly n different eigenfunctions, and if all of them are localized, I can do this operation, so to take the linear combination of these wave functions, and then we know what happens. It will be an extended wave function. This is the way to produce extended wave function in condensed matter, for instance. And on the other hand, if I look at this linear combination, I can think of it as one wave function which is obtained by a rotation of the basis. So in the initial basis, all wave functions are localized. But when I take such combination, it is just one wave function obtained by in a different basis, which is rotated. So this is a very high dimensional space because if the matrix size is large, so this is a Hilbert space, n-dimensional. And what this simple example tells us, it tells us that localization is not basis rotation invariant. So if in one basis we have localized wave function, then suppose that all of them are localized, then you can do such operation that means rotating the basis in the Hilbert space, and then you will have extended wave function. So this is actually a great difference between the spectrum eigenvalues and eigenfunctions, because spectrum is invariant under rotation of the basis, and eigenfunctions are not. So this is something which people have to keep in mind, because when I it is often said that if the wave functions are localized, then there's no level repulsion. And if they are extended, then there is level repulsion, which we have been talking last time. But this statement is actually mathematically incorrect, because you are comparing something that depends on the basis rotation with something that is invariant. So therefore, nevertheless, you will hear this statement very widely that the localized wave function do not have the level repulsion. And so how one should understand that? One should understand that in the following way, that among all the bases in the high-dimensional space, Hilbert space, there is a special basis in which localization may happen. So, and it is, and then if there is such a special basis in which localization happens, then this only fact is enough to say that the spectrum will be Poisson with no level repulsion. So, and this is actually quite a deep statement, which is important if people start to think about interacting system with very big Hilbert space. And so it is kind of
in principle, in this random matrix theory of Wigner and Dyson, well, eigenvectors and eigenvalues, they're decoupled. Because eigenvalues.
Sure, we will be talking about that.
So this argument about eigenvectors in somehow.
No, it is only when Wigner Dyson doesn't hold. Because, as I said, if there is localization, forget about Wigner Dyson.
Yeah, that's what I'm saying. Why I should forget about Wigner Dyson if in some sense this stuff doesn't tell me anything about eigenvalues, right? It just tells me about properties of eigenvectors, and there's another thing which is eigenvalues.
Right. But what I'm saying is the following: that if in some basis you have wave functions such that at one energy it is localized here, at the other energy it is localized there, in the first energy it is localized here. These are all wave functions that correspond to some to some level. But if you take the linear combination, if you rotate the basis, you doesn't change this eigenvalues. You change only eigenfunctions.
But even this, for me, it's hard to say because, okay, you say about existence of some basis. Okay, I can always take eigenbasis and we will localize. Okay. So
No, there is one very good question. So there is always one special basis, which is the basis of made of eigenfunctions, right? And in this basis, of course, everything is localized because if you take eigenfunction, it will remain eigenfunction forever, right? So there is one special basis which where there is always localization, right? But the statement that I want to make, thank you for this question. The statement that I want to make is the following: that this basis made of eigenfunctions, it depends on the realization of disorder. It depends on how exactly these scatterers are arranged. Okay? What I'm talking about some basis that doesn't depend on the realization of disorder, and that's is non-trivial. That is, this is non-trivial. If there is a basis which doesn't depend on the realization of disorder, but depends on some other average properties of the Hamiltonian, then if in this basis the functions are localized, then eigenvalues should be Poisson distributed with non-level repulsion. This is the exact statement. In some sense, you know, this is like a Galilean invariance. So, you know, what is the first Newton's law? The first Newton's law states that if we are considering dynamics in inertial frame, then without applying a force, there will be no acceleration, there will be straight and motion with constant velocity. But in fact, this is a concept. This, we know that this inertial system doesn't exist, so it is an idealization. So, you know, if I'm here on the ground, it is more inertial than if I'm in an accelerating elevator, for instance, right? But on the other hand, this Earth at this point is rotating and it is not exactly inertial. So it is just the proclamation that there is such inertial frame in which second Newton's law holds, right? Here, something similar. So there is a statement that in a very multidimensional space, there is such a frame. If eigenvalues are Poisson distributed, then you always can find such a frame. If they are not Poisson distributed, then you will not find the frame in which eigenfunctions are localized, but you can find later on. I defined what is fractality of states and what is fractal dimensions, and then the fractal dimensions of the localized state is 0, and the fractal dimension of the fully extended state is 1, and there are some situations where the fractal dimension is between 1 and 0, and then the statement about the special basis is the statement that in this basis the fractal dimension is minimal. So you can always make it larger because you can make extended states with fractal dimension 1 out of the localized with the fractal dimension 0, just by rotation the basis. So it is possible to make it to make this statement extended to a continuous variable, which is fractal dimension of the wave function, and that this is later on.
So, but can I?
Now, again, down to the earth. So,
So you want
Anderson-
Can I ask one more question, please?
for
Just
explaining
Can I ask one more question?
local, yeah.
Sorry. Just about. Can I ask you about this kind of physical meaning of this basis? So on the picture before you had in mind some kind of space basis. So we have a localization in the space, right? Because in this
No, it's not a space basis. It is the basis is the following. So suppose you have some vector, right? And then when you change the basis, suppose you are living in a very high dimensional space, right? And you have a vector with many components. Now, then it is possible to rotate this basis in this high dimensional space. This is not the space in which localization happens. It is the space of functions. This is Hilbert space. The space of functions. And so any linear combination with the proper choice of angles, right? Because rotation, there is in multi-dimensional space, there are many angles, right? So these coefficients can be interpreted as corresponding sine, cosine, and their combination of such angles. So it doesn't have anything to do with the real space. It is a space of functions.
No, you just said that there is a localization in a particular basis. In a particular basis that is not dependent on the disorderization, right?
Yeah.
Now I'm asking about
But this is not trivial statement. I mean,
of course. I'm asking about what is the physical consequence that it happens in this basis, because I can imagine if this is happens in the space basis, I have some kind of transport. I know transport is localized as well, right?
okay. So let us first of all, nobody knows how to find such a basis in general. So in some simple cases, it is easy to find. For instance, sometimes eigenfunctions are localized in the real space, and sometimes they are localized in the momentum space.
Yeah, exactly.
So this is a simple.
Yeah, and the physics is very different, right?
Yeah, this is physically simple. So if you take, let's say, random matrix, which elements depend on the difference from the diagonal, then you can do Fourier transform and define momentum basis, and then you essentially should choose between the basis in which this matrix is formulated and then the basis of. Okay, so look.
Yeah, maybe I can ask.
We'll go because it will be then conversation between me and you.
No, I understand that.
Because there are different levels of complexity here. So sometimes I'm drawing deep, but I cannot, stay always on that depth. Okay, look. So when a simple Anderson localization was actually the initial work by Anderson was about semiconductors and three-dimensional case electrons in this three-dimensional case, then at low density, then there is a lot of impurity bands and things like that. But the model was very simple. So it was a lattice, and let's say 1, 2, I mean 1 and 2 came later. So the first was three-dimensional lattice, and the tight binding model in this lattice. So this is a hopping to the nearest neighbor, and this is the random on-site energy. And this is known as Anderson model. Anderson himself considered distribution of these guys in the form of rectangle, but it is possible to consider Gaussian distribution. And this guy, for simplicity, was considered constant. Later on, people ask a question: what will happen if this is constant, but this is a fluctuating stuff? And this is a different model. In the Russian literature, it was proposed by Ilya Lifshitz, and in Russian literature, it is known as Lifshitz model. But later on, people understood that if there is only hopping to the nearest neighbor, and this guy is zero or constant, doesn't matter, and the entire disorder is here, then there is a special symmetry, which we will be discussing next time. So this is a different model with some peculiarities. But initial one was the side disorder, and what is known, I mean, I think most of you know that in one dimensions all states are localized, and the localization length is as simple as that, where W is the width of this distribution. This is for rectangular distribution. For Gaussian, it will be a bit different number, and here there will be the variance of the distribution. Then in 2 dimensions, all states again are localized, but now localization radius is exponential in this disorder, so it is much weaker localization at weak disorder. And in 3-dimensional case, there is a transition. So if W is smaller than something, then if this is 1, W should be 16.5 or 16.5 T. If T is not 1, then there is the transition from extended to localized state. And this transition is very interesting because exactly at the transition point and in the vicinity of it for finite system, there are very interesting critical states which I hope we will discuss. Now, this I have already told many times, so if we have extended states, then there is level repulsion, and this distribution of spacing behave like this. If states are localized, with this comment that I made, localized in some frame, in some basis, then the level repulsion doesn't exist. So at zero spacing, the probability density is constant, and then it falls down. It falls down exponentially as a simple exponent, and this falls down as a Gaussian situation. So we will derive this formula later on. This is the following. This is just the result of numerical calculation done actually in the 90s, long ago. And now, of course, there are other objects and better accuracy, but this is the first calculation of this type. So this black curve is the result of random matrix theory for spacing distribution. And the green one is the result of the Anderson model at W equal to 5. Now, then, if you have very large W equal to 100, then this is a blue curve and it is very close to Poisson. But if you take the critical, this is three-dimensional case. If you take the critical one, then you will have something which is closer to Wigner-Dyson than to Poisson, but it has some deviations, and this is known as critical level statistics, which are very interesting in general. So then, approximately at that time, people suggest how to identify where transition happens. And the proposal was very simple. Take the spacing distribution and find the variance of this distribution. So every square of spacing. Every spacing here is 1, but every square depends on the shape of this curve. So take the variance and see how does it behave as a function of disorder in three-dimensional case at different size of the system. So at that time it was 28 by 28 by 28. But now, of course, people do 100 by 100 by 100.
Sorry, very naive question, but when I look at the left plot,
Yes.
there are points on the blue plot for the insulator,
Yes.
at the left part, where it goes like to 0.
No,
Like there is-
You mean this point?
No, the blue ones, which are like.
Yeah.
yes,
Very
so-
good question. Very
okay.
good question. So the thing is that indeed, if you look at those points, you will see that there is some signature of level repulsion, and in fact. What happens is the following, that when this is simulation at finite system, and when system is finite, two localized states are not infinitely far from each other. So they exponentially overlap, because there is a tail of, so one wave function is like this, the other is like that, but if I see here, there is some exponential overlap. And this exponential overlap leads to some level repulsion, which disappears when you go to infinite size. Because when you go to infinite size, then typically they are in a different corners of the system, and this, so this is a finite size effect. Now, good question. So then okay. So what is here is the variance as a function of disorder for different system sizes, quite small by now, and you can see that all of them approximately intersect in one point. And so that if your disorder is weaker, then with increasing size, the variance goes down, and here it is going up. And it is the simplest way to identify the transition point. So for this sake, the eigenvalues are very, very useful. And now the rare picture which
Can I ask?
now nobody
So what do you
really
think?
remembers,
Can I ask
and this is the following.
Sorry.
Can you Can I go back to can you go back to the previous plot? So what at the thermodynamic limit, what you expect for the right curve is to be a step function, something like that?
In the thermodynamic limit,
Should it be like
here it definitely let me understand. So suppose that the disorder is larger than the critical, then all states are localized, and then your distribution approaches Poisson. Poisson distribution has a certain variance, which is certain number. So this means that if you increase the system here, it will go up, but then it will saturate because this has some certain variance. So if you, on the other hand, go here, it will also saturate because the Wigner-Dyson distribution has also some constant. So it is some dynamics. Possibly you have to have very large system because, as I said, it is the system which is 1,000 times smaller than people can do now on the computer.
And how can I ask? So actually, at this critical point, nothing moves. But this is because you're lucky, no? So
critical point should not move because I mean the thing is that if you are at a finite size, of course there is not an exact intersection here because there are some finite sizes here. But if you go to the thermodynamic limit, that intersection becomes better and better, and it should stay. Why? Because in the critical point, you have size independence of everything. And this is the main idea. So that if you are in a critical point, then your finite size corrections are much weaker than if you are beyond of it. Okay, so let's go because otherwise I will never finish. So this is the picture. The following one. Take three-dimensional sample under the model. Then take some realization of disorder, so random on-site energies. And then what you only do is to increase the scale of disorder. So suppose, I mean, I show you. So suppose you have on-site energy which behaves something like this, very in a complex way. But then what you do, you you simply scale it like this, repeating all the features. So there is only one parameter, is scaling of this on-site energy. And this parameter is shown as W here. And you see what happens. So even, knowing anything about matrix and transition, whatever, you see that there is a qualitative difference. What is this line? And these lines are the energies of the corresponding level. So I change, I scale this random potential, and of course energy moves. So as I increase disorder, energies move. And the other energy level also moves. So you have spaghetti of different energy levels, which depend on disorder. And then you see on this picture, and you see that there is a qualitative change here between this and that. And what is this change? This is level repulsion. So if you magnify this picture, you will see that that this pattern on the left it avoids the crossing between. So there is of course statistics of these gaps, but in principle there are small gaps here. There are large gaps. I don't know, over there. But there are always these gaps, and if you have a localized, the same happens for chaotic billiards. If you have localized system or you have an integrable billiard, then there is plenty of intersections, so level repulsion is not there. But there is more than that. So you see, there are some strange traces here, which actually, people looking at that picture, they of course took note about level repulsion or the absence of the level repulsion. But to the best of my knowledge, nobody addressed these lines, and then this picture was forgotten. So, it is 40 years old. And if you look at, so basically, this is some global feature of such spaghetti and their intersections, which is not only in this picture, it is present in all pictures. And I always sort of put a question for myself how to describe it, but to the best of my knowledge, nobody did it so far, although it is quite spectacular. So this is just something which is left understudied. Okay, so let us, I explained more or less what is Anderson localization in a very short introduction. And now let's come back to random matrices and ask a question. Okay, so we had classical random matrices in which the distribution of the Hamiltonian has the form like this, with a constant variance. So variance does not depend on the entry. Entries are all independently Gaussian variables, but the variance is the same. So I depict it like a matrix with a homogeneous background, which is just the variance. It doesn't depend on the entry. Now, and as we know, this stuff is invariant under basis rotation. But now we know that in order to describe localization effects, not only strong localization, but any localization effects, you have to break this rotation invariance. And one simplest way of doing so is to retain the Gaussian nature and independently fluctuating entries, but make the variance dependent on the distance on the particular n and m in principle. So one simplest way and trivial way of obtaining localization is to say that there is no hopping at all. So this is the diagonal matrix. So if the matrix Hamiltonian is diagonal, then you simply create the wave function which is only on one side, and it will be the eigenfunction. So it will not evolve anyhow, and then we see that there is an extreme localization on one side. So, but then you can do localization which will be not on one side. You know, the diagonal matrix means that this variance is, for instance, one way to do it is to have an exponential dependence on n minus m, but say that this psi localization radius goes to 0. So when it goes to 0, there is just diagonal matrix, and everything is localized on one side. But then you can make this psi finite, and then you will have a matrix which variance will be in some strip, and this is so-called banded matrices, and the properties of eigenfunctions in these bases, in the basis where it is formulated, where there is this probability distribution. In this basis, you will have eigenfunctions like in one-dimensional system. So they will be all localized, but with some finite localization legs. And if you make this thing bigger, then the localization will be weaker, but nevertheless our state will be localized. So it was possible to show that such banded matrices are equivalent to quasi one-dimensional system. So the wires, and this is the extreme case of localization, but there are other ways to break rotation invariance, and one way is extremely simple. So you take the Wigner-Dyson matrix, which is the gray pattern here, all the variances are the same, and then add to it a random diagonal matrix. So it is just a hybrid of Wigner-Dyson and random diagonal matrix. And this model is suggested in 1960 by Rosenzweig and Porter, and it is known as Rosenzweig-Porter model. So the simplicity of this model is the following, particular simplicity, is that if you subtract this diagonal matrix from the Hamiltonian, you will have Wigner-Dyson matrix. And Wigner-Dyson theory, as you will see, is to a large extent exactly solvable. And then what you, in order to solve this system, in principle, what you have to do, you have to solve Wigner-Dyson, but it will be dependent, the result will be will depend on this matrix which I subtract. And then I have to subsequently average over this diagonal matrix. So it was done in this way, exact solution, and so this is a good way of breaking rotation invariance, because this model is so simple that could be solved exactly for many quantities of interest. So the thing, but it is not because of its simplicity that it is interesting. The point is the following, that it appears that in this model there is not only localized phase and extended phase. So if I say that this sigma is something like n to minus gamma, where n is the size of matrix, and gamma is a parameter. Then when I change gamma, it appears that there are two points, gamma equal 1 and gamma equal 2. And here there is a delocalized, random, Wigner Dyson matrices. Here there is localized phase. But it appears that there is some special fractal phase here, and this was actually overlooked for, I don't know, rediscovered this thing in 2015, and the model was suggested in 1960. So I will be discussing then what means fractal eigenstates, but this is the simplest model where such thing can be observed and studied and made rigorous, like in a mathematical sense.
Sorry. This sigma is just the sigma which stands near H0.
This one.
Yes, okay. And epsilon 1 to epsilon n, they're random.
This is the diagonal
Yes.
matrix with uncorrelated random variables.
Yes, but they are like of order of 1.
Yeah, it is of the order of 1. But it appears that in such matrices, you see, if diagonal is of the order of 1, then and there are n diagonals, so there are n diagonals of the order of 1, and there are n squared of diagonals, which are of the order of n to minus gamma over 2, because this is gamma. I'm sorry. Okay, and then what you can say that just looking at that, you can say that if gamma is very large, then off diagonals, effect of off diagonals are small compared to that, and then we have the same situation qualitatively as if off diagonals are absent whatsoever. If gamma is small, then the situation is opposite. But non-trivial thing is that in between there is something non-trivial. Okay, I hope you will find time to discuss it in more detail, but this is an interesting model and very simple. So for those people who know about glass theory, glass theory is the following. People take spins, classical spins, and then say that there is a random interaction between these glass spins. Random in sign, random in the amplitude. And what happens at some temperature with this model is that this model becomes like a glass, so it becomes rigid, and there is a very well known model for such one-dimensional glass, which is exactly soluble, and this model is known as the Sherrington-Kirkpatrick model. What a Sherrington-Kirkpatrick model is when any spin interacts with any other spin with some random interaction. So it is like here, it is hopping from any side to any other side with the random amplitude. So that problem was a classical problem, and it was solved very non-trivially by Giorgio Parisi. He did very sophisticated replica symmetry breaking and solved this problem. Now, here the solution is more simple because usually quantum mechanics is simpler than the classical. But this is the other thing. Now, then, what can also be of interest? There is also a rather simple way of breaking rotation invariance. And this is to make the variance, this is not that sigma which is here, rather this is sigma which is there, which is the variance. And so one way of breaking rotation invariance is to say that this sigma behaves like that. So it is, there is a parameter b here, and this is n minus m difference from distance from the diagonal. And you see that if this n minus m is bigger than b, then there is the power law decay of the variance. And this power law decay of the variance is controlled by this parameter a. So there are two parameters b and a. And what is known about this model? This model is called power law banded random matrices. So what is interesting about this model is the following: that it has this model has a transition from extended states to localized state, and this transition happens at any b at a equal 1. So if a is smaller than 1, then the fall down is weak, and then it approaches, in some sense, Wigner-Dyson, and there is a delocalized, there are delocalized wave functions. If a is large, then it is very steep decay, and it approaches the diagonal matrix or banded matrix, and in this case all states are localized. But there is a point where a is equal to 1, so when this decay is exactly 1 over distance, 1 over distance in the square root of sigma, so the sigma 1 over square of the distance. And in this case, there are states which are fractal, but not only fractal, they are multifractal. So this is something that I hope we will also discuss. So this very interesting, but this model models what happens in particular in the critical point of the Anderson transition of the Anderson model, which is very physical, tight binding model with on-site disorder. And this is not very physical, I would say. But what is very interesting that if I take a equal 1 and then study different statistics of eigenfunctions, of eigenvalues, everything that I can do, I find the quantitative correspondence with the three-dimensional Anderson if I choose the parameter b properly. So for three-dimensional Anderson with time reversal symmetry, it is one b. Without time reversal symmetry is the other b. But very surprisingly, such a model which is only chosen from the condition that At a equal 1, it is a critical model. It describes Anderson transition in 3D, and also, as far as one can check by numerics, also in 4D and 5D. Of course, the numerical accuracy falls down, and one cannot say it with certainty, but this is the case. So this is, in some sense, this model is, you see, if I set here A equal 1, as I said, it will be describing Anderson localization transition point, what happens there. But then one extra parameter B still remains, and so in some sense this model at A equal 1 can be considered like a proper deformation of the Wigner-Dyson model, because when B goes to infinity, this term becomes becomes 0, and except for n equal m. And then we have simply, I mean, also when n equal m, it will be 0 as B goes to infinity, and then the variance become constant, and this is Wigner-Dyson. Therefore, it can be it can be considered, at least at large values of B, like some departure from Wigner-Dyson, deformation of the Wigner-Dyson in a proper way, and it is very interesting, with very interesting property, with connection to other theories and so on.
Just two questions. First, so do I understand correctly that this is more or less like 1D lattice model?
Yeah,
with
long-range
hopping, and it is in
Absolutely.
correspondence to the 3D Anderson model.
Absolutely, it is one
Okay.
model with long-range hopping.
And what do you mean by correspondence? What kind of quantities do we compare?
No, what I meant is much less trivial what you say, because this is one-dimensional model with long-range hopping.
Yes.
So, it is known long ago that if you have long-range hopping, then you effectively increase dimensionality. Because, you know, dimensionality only matters when you have short-range hopping, because then you have topology, then you, but when you have long-range hopping, you scramble your one-dimensional space, and effectively it becomes it becomes not one-dimensional but high-dimensional.
Okay. Okay.
And in high-dimensional space, we know that there is a transition. So, and we know that there are delocalized states. So this long-range hopping is actually the spin models are well known with long-range hopping, and they have completely different properties compared to short-range hopping. So, but what I meant is different, because this is the model with long-range hopping in 1D. And I compare it with three-dimensional model with short-range hopping.
Yes.
So, you know, of course, we know from intuition that making long range effectively increase your space. But that it increase properly or not, we don't know, right?
Yes.
But what I'm saying is that there is a quantitative comparison, which is very good.
Yes. This is the question. What exactly they compared? Some correlators or
exactly. Look, I will.
Okay.
I will come to that. Level statistics we compare.
Okay.
Okay. So then, one next step, and this is extremely interesting model, which is, to my understanding, is not. I mean, the study of this model is in a very initial stage. So this is the following thing. First of all, just this is so-called ultrametric random matrices. The definition is the following. So, by different intensities of the color, I depicted the value of the variance. So you subdivide your matrix by blocks. So there are small blocks, then 2 times bigger blocks, 4 times bigger blocks, and so on. And let the size of the block will be L 2 to n. So the smallest one is 1, and this is diagonal. Then okay, then the maximal distance in a block from the diagonal is of the order of this L. L times square root of 2, something like this, of the order of L. So here it is big, here it is smaller, here it is even smaller. Now, then the definition is that the variance of this matrix, it is again Gaussian, independently fluctuating entries, but definition is that the variance, if L is 2 to n, then the variance is some number p to minus 2n. So in order to understand better, let us do the following. Let me express this variance in terms of L. And it is done in the following way. So there is some strength, and then there is L to minus 2a, where, and if I compare with this, I will find that P is 2 to a. But what is it? It means that L, as I said, is the typical distance from the diagonal here. Okay? Now, then, if the variance behaves like a power law of the typical distance, it is more or less like this, where is the distance and also to a power law decay. So then, looking at this model, I see that somehow the typical, the variance depends on the typical distance in the very same way, like for power law matrices. But A is expressed in terms of this P. And now we know that the power law matrices, there is critical A equal 1. And then there is a special statistics and all these things like the critical point of the Anderson transition. And here, A equal 1 will correspond to P equal 2. And indeed, when this model was studied just properly, it was found that there is in this model there is a critical point at P equal 2. But so to the first glance, this model is some pervasive variant of the power law banded matrices. And actually, I had the same opinion for a long time. But now I changed my mind, and now I see from some numerics, which I cannot go deeply in it, I see that in principle the general statement is that at the critical point of Anderson transition of these power law matrices, there is some sort of so almost all the distribution functions are power law, like in the critical point of second order phase transitions. And moreover, there is some structure in the statistics of wave functions which is similar to what mathematicians called counter set. So this again, if there will be time later on, I will tell you what is it. And it appears that such strange construction that mathematicians do. So what they do, they take the segment from 0 to 1, and then they take 1/3 of that, and then they take 1/3 of this, then they take 1/3 of this, then they take 1/3 of this, 1/3 of this, and you have a hierarchical structure. Okay, and you can say, well, let I pretend that these are energy levels of some system. And then I can ask a question: what will be the density? What will be the density correlation function, and other things? And it appears that there will be, of course, power laws, but those power laws follow from this hierarchical structure. And then one can compute the fractal dimension. So I can say that okay, so this thing has a fractal dimension. So in analysis of the first year of analysis, mathematicians usually show that as an example, a curious example. But it appears that this curious example is realized at the critical point of the Anderson transition and at the critical point of such random matrices, which are, of course, much easier to study than the Anderson model. And what I want to say that this peculiar power law power law matrices, they have the hierarchical structure. Never ask where, because I have to then make several lectures on that. They have hierarchical structure which is sort of much cleaner than the one which is in the critical point of the Anderson transition and in the critical point. So the power law are better. It follows from numerics. And this means that perhaps this model is exactly solvable and free of some unnecessary or unwilling features like the Anderson model and the power law matrices, which the usual are like this. So therefore, it always, it frequently happens so that you make the model apparently more sophisticated, but the solution of it will be simpler than the model. And this is what I suspect very much about this model. This is not done in, this is only the hint from numerics. Okay, so by the way, I told you about spin glass and about solution of this spin glass model by Parisi. And the solution was in terms of replica And the construction of the replica symmetry breaking was exactly like this, but this was not a Hamiltonian, of course. This was the matrix n by n, where n replicas were necessary to introduce in order to treat disorder in that. So you see, this thing, it has apparently some common structure and, let's say, glass physics, and it has the common structure with fractal objects in mathematics. Okay, so now what remains is basically half an hour. Oh no, half an hour we don't have. Okay, so I'm done with the introduction. And the goal of this introduction essentially was to tell you that having a proper random matrix, you can model real world. But of course you have to define a proper random matrix for describing Anderson localization. They are different from those who are describing just only situation where there is no localization effect. But it is also interesting that there are phase transition happening in such random matrices, and there are special critical statistics of eigenfunctions, of eigenvalues, which resemble very much, they are of course not identical in no sense, but the problematics is similar as the problematics of phase transitions of the second order. In particular, there is an open question about conformal field theory. So you know that the most powerful tool to study criticality in phase transitions in two-dimensional phase transitions are conformal field theory. So now there is conformal Booth-Street, which allows to use conformal field theory in systems of higher dimensions. And since the transitions in this random matrices with no basis rotation invariance are very rich in that sense, but still there is a feeling that there could be some generalization of conformal field theory that would apply for such transitions, but it is absolutely unknown for the simple reason that somehow people like Polyakov, Lavin, classics of the conformal field theory, they know nothing about disordered systems and these problematics. And people who know something like me are probably not equipped with the knowledge of conformal field theory necessary to do something serious. And not speaking of people who do numerics, numerics is important because it gives some hints, but of course there is a feeling that many of these models have a structure that allows to go deeply beyond with some mathematical tools, as I said, like conformal field theory or its variants. For instance, since I have no time, therefore I will not go for more simple stuff. I want only to say that there is a special Anderson transition, Anderson in some quotation mark, transition in the system, which is electrons in the strong magnetic field. So it is problem of Landau bands, but in the presence of disorder. This is the problem of quantum Hall effect. And when you change your magnetic field or you change your density, then so the Landau level for the clean system, it is broadened in a disordered system. And right in the center of Landau band, where is a jump in the Hall conductance, according to integer quantum Hall effect, exactly at that point you have a transition in a sense of Anderson, but the transition is such that here is insulator, here is insulator, and here is the critical state. So there is no truly extended state, but there are insulators on both sides, and the critical state here. And the properties of this critical state was the most discussed by people who are close to mathematicians. For instance, Martin Zimbauer, who was the main actor here, he suggested what exactly conformal field theory describes this transition. So I even cannot reproduce it. It is there's zoom in of some level, blah blah blah. But Zimbauer did very precise statement about that, but not the derivation. So derivation was floppy, and the discussion is still there, and numerical people try to increase numerics in order to check predictions, because there are predictions of what is the value of sigma xx, sigma xy, in this case, if conformal field theory works, and also about level statistics. So no accuracy of numerics is enough to prove or disprove, but the numbers are really close to those which conformal field theory of that type predicts, and the difference is as small as 10 to minus 3. So one has to do numerics, let's say, on different correlation functions of level statistics with the accuracy 10 to minus 4 to say whether. Still, there are people who are playing this game, and they have fun of that. So what I'm saying the following, that that there is a number of models, like Anderson model, like the model of Landau bands with disorder. Then there is some very popular model of that transition, which is called Chalky-Coddington model, and So, and then there are all those models have some critical states and some peculiar properties of that, and random matrices too. And it is interesting to find out what is the common structure. So, of course, if someone says that everything is completely universal, it will be a person who is lying to you. But on the other hand, always to find something in common for apparently different models is a noble task. And this is what I'm trying to do myself, but certainly the attention of people who are more familiar with things like componency theory is very welcome. So, okay, I wanted to start this stuff, but this is, what I'm doing is a mixture of standard things that you can read in standard books on random matrix theory, and some extensions which are broad enough and floppy enough, but still I just want to tell you that this is not like, like a narrow part of mathematics which you just learn and then you don't know where to apply it. I want to tell you that this is the problematics which are very much open, and the complexity appears exactly when you break your basis rotation symmetry. And nevertheless, it is not hopeless to deal with such model. Mathematicians, strict mathematicians, those who do rigorous calculations, they just raise hands and say, well, we cannot. But for physicists with good mathematical background, this is not a hopeless thing to find something which, especially about the critical statistics. And therefore, I just want to tell you that this is a field which is alive, which is not only something which you may apply, let's say, to distinguish the healthy brain from the unhealthy one by signals. And this is something which has a fundamental value. Okay, anyway, so I think that I will finish today because this is the part which is the standard random matrix theory of Wigner and Dyson. And so, as I said, I want to tell you some knowledge about the standard things, but also some, overview from above over what is possible to do in this field for young people. So this is it. So I don't know how fast I will go, and therefore I gave this introduction to all these peculiar models in order you know about them. In case you will not